Thanks so much. It's a pleasure to be here to share the work that we've been doing over the past 20 years and our hopes for the future. So I had a presentation that is failing to upload, so I'm going to do this without slides, which is an interesting challenge for an astrophysicist because we're all about the visuals. But let me just start with saying I am an astrophysicist, so my job is to study the universe. And we ask the biggest questions. We ask about how the universe begins. We ask about the potential for life elsewhere in the universe. And my favorite topic is we ask about black holes, which are the least understood objects in our universe. And I've been doing this for 20 years, studying black holes with, as Jamie said, with the Keck telescopes. The Keck telescopes are why I'm a professor at UCLA. I have what I consider to be my dream job. And it's my dream job because UC and Caltech own the largest telescopes in the world. So as an astrophysicist interested in studying the universe, having the best technology is what allows you to be at the forefront of discovery. So being a university professor at Caltech or the UC system puts you at that frontier. Now, UCLA in particular saw an opportunity to take the lead in this consortium because they recognized that infrared technology was taking off at the time that this telescope was being built. Infrared technology is, of course, really important to the military. It's developed in Los Angeles. So, in fact, UCLA as a campus in this partnership, it made a lot of sense for us to invest in infrared astronomy. So infrared is light, which is just long word of what your eye detects. It's where your TV remote control works. And I'm an infrared astronomer, astrophysicist. And that's why UCLA hired me. It was all part of this vision that they were going to take over the infrared at Keck Observatory. Now, to give you a sense of scale, Keck Observatory is a major investment for the university. These telescopes, and there are two of them, are a $180 million investment, capital investment. And the operation cost of these observatory is $100,000 per night. So you can see why that as a resource is an incredible resource that the University of California gives its astronomy and astrophysics community. And because the University of California has always invested, or not always, for the last 100 years, and from the university perspective, that's a pretty long time, in having the largest telescopes in the world. In fact, UC has roughly 20% of the entire field of astronomy and astrophysics in universities. So we are a big player in this field. And I've been there for 20 years. So when I got there, my shtick was I wanted to develop new methods for using this telescope. And in particular, new methods for getting the sharpest pictures from this large ground-based telescope. So the promise of large telescopes, in some sense there's really two campaign promises that big telescopes make. One is, and by big I mean the size of the mirror. So we quantify or characterize the size of a telescope by the size of the primary mirror, the mirror that collects the light. So Keck is a 10-meter, it's actually two 10-meter telescopes. And to give you a sense of scale, 10 meters is the width of a tennis court. And in fact, UC came up with innovative technology that allowed mirrors to be built at that size. In fact, in the early days, people said it could not be built, and yet it was. And all future telescopes have been built with this new architecture, which is segmented mirrors. Okay, so we have a 10-meter telescope. That's great. There are two campaign promises. And the first campaign promise is that you build a big telescope because you can collect a lot of light. So you can think of it like a rain bucket. It collects light raining down, so that means you can see things that are faint. And in astronomy, faint usually corresponds to things that are far away. So you can see the distant universe, and because light has a finite speed, that corresponds to the early universe. So if you want to understand the origin of the universe, you want to build as big a light bucket as possible. So that's been a big driver for big telescopes for the last 400 years since Galileo made his first telescope. Now, there's a second campaign promise, which is the thing that I find quite interesting. Okay, are we going to do this? I don't know where I am in my presentation, so I think we're going to keep going this way. Oh, we're there. Those are the telescopes. So those are the two Keck telescopes. Those are the domes. And the lasers coming out are actually this development of this technology that I'm just about to get into. So the technology is the key technology, or let's see, so we want to get to the highest resolution. In other words, the big telescopes allow us to see as fine a detail as possible. The bigger your telescope, the finer the detail that you can see. In principle, but the challenge for ground-based telescopes has been the atmosphere. Great for us, but a complete headache for astronomers. As you might imagine, actually other people care about looking up and down through the atmosphere. The military does. So there's been a lot of technology sharing once various things have become declassified. So my shtick when I got hired by UCLA was I was really interested in developing techniques to get the sharpest images possible with the largest ground-based telescope. So we made the first, what's known as diffraction-limited pictures from this observatory, which was a factor of 20 in improvement in your ability to see detail. Now, my science that I'm going to share with you goes as your resolution, your ability to see fine detail, to the 4th power. So that's a pretty big gain. In fact, it beats anything that we can actually do in space. Okay. So we've used this over the last, the last 20 years to look at the center of the galaxy. And the question that I was interested in initially was the question of, can we prove that supermassive black holes exist? You know, we assume they do. And they're a key component of our models of how the universe works. And yet we don't have evidence, good evidence, that they exist. The ability to take sharp images has enabled us to prove, to actually come up with the best evidence to date that supermassive black holes exist. In fact, it's improved the argument by a factor of 10 million. I mean, think about any advancement that you can make that has a factor of 10 million in front of it. And then you would realize why this has been such an important advancement. This has been done because we can measure the orbits of stars at the center of the galaxy. And this has opened up not only the best proof, but actually a brand new way of studying black holes. So today, we have a project that is known as the Galactic Center Orbits Initiative. And it builds on this initial work with high-resolution imaging, your ability to see detail, fine detail with large telescopes. And our objective is to use the measurements of orbits that's now possible at the center of the galaxy to test, to understand, well, what is a black hole? What is the complete theory of gravity? Black holes represent the breakdown of our theories of gravity. I'll get into this in a second. And these orbits allow us to explain what a black hole is. It also allows us to look at what role black holes play in the formation and evolution of galaxies, which are a key component of our universe. All of this is really driven by technology and advancements in methodology. So there are two key aspects of the technology. From my perspective, there's the ability to see, to make precision measurements. We're interested in the distant universe. We cannot go there. So our laboratory is the center of the galaxy. It is 26,000 light years away. That means it takes light 26,000 years to get from there to here. We are not going to this laboratory directly. We are studying it remotely. So the ability to make precise measurements is essential. So we drive a lot. We work very hard on technologies and methodologies to improve our precision of measurement. And then we collect a lot of data. And we are in the era of big data sets. And this is an enormous data set that we've collected over the last 20 years. So we develop a lot of big data analytics that allows us to study the stars, thousands of stars, as they trace their orbits through this 20-year data set. So it's precision measurement and big data analytics from a technology and methodology perspective. And then, of course, there's an educational component. We do a tremendous amount of public outreach to excite the general public about science, because black holes are cool. If you've seen Interstellar, you understand the excitement and fascination with black holes. We're also interested in training the next generation of students on this new technology, both the precision measurement, and of course we can contribute in big data analytics. And then last but not least, if you haven't noticed, there are very few women in the field of science. And so we do a lot of work towards encouraging young women into the field of physics and astronomy. All right. Now, I did this a little out of order, so I actually need a little time stamp on me. How long have I been going? Oh, thank you. That's my countdown. Perfect. OK. All right. So perhaps we should say what a black hole is, because we've been talking a lot of about black holes. A black hole is an object whose pull of gravity is so intense that nothing can escape it, not even light. So it makes them relatively hard to study. So that means you can't see anything, and hence the blank cell-eyed. They also represent, the way I think about black holes is you can think of it as a mass which is confined to 0 volume. So if you think about density, which is mass divided by volume, that means that density is going to infinity. And in physics, anytime you have a quantity going to infinity, it's known as a singularity, which is like a big red arrow that says you do not have your description of the physical world quite right here. And our problem or our challenge or our dilemma is we don't know as scientists how to make Einstein's wonderful theory of gravity, general relativity, which is the study of gravity, things with lots of gravity, and black holes certainly have them, work together with quantum mechanics, which is the study of things that are very small. And black holes are absolutely small. So we do not have the mechanism or the field, the models to make these two fields work together. So when we understand how to do that, we'll understand what a black hole is. But fortunately for me, there's something that there is a size that we can associate with black holes, which is known as the Schwarzschild radius. And it's the last point at which we can get any information about the black hole. And, and once you prove that there's mass inside its Schwarzschild radius, you've proved that there's a black hole there. Because at that point, gravity overcomes all other known forces, and its force becomes an infinitesimally small object. I'm going to quickly go through this. If you could squeeze the Earth into the size of a sugar cube, it would become a black hole. If you could squeeze the sun into the size of, I had to do this, UCLA's campus, go Bruins, it would become a black hole. OK. So you have to work on very small scales to prove that there's a black hole and to study these things. I'm going to skip this because I don't have time to do this. So there are we think that black holes exist at the center of galaxies. That's just an assumption that has been made for decades. And we think that they're intimately coupled with how galaxies form. If we could get outside our own galaxy and look back, this is what our Milky Way, which is the name of our own galaxy, would look like. And in fact, I think it's worth commenting on. 100 years ago, we thought the entire extent of the universe was the Milky Way galaxy. Our knowledge of the universe has expanded dramatically in recent times. So we had the galaxy. We live about halfway out in one of those spiral arms. So as I said, the center of the galaxy is 26,000 years. Now, if you want to study supermassive black holes, we think those things are at the hearts of all galaxies. So that's the supposition that has not been proven. And our galaxy is certainly the best place to look. It's the closest center of a galaxy we will ever have to study. It's in our own galaxy. So this is a picture that's taken from the Mauna Kea, which is in Hawaii. Which is where our telescopes are. And we live in our galaxy. So looking out, the galaxy is a flattened disk-like geometry. We see that plane of the Milky Way. That's and so that's all that white streak is all the stars that exist at the center of the galaxy. And in fact, not only is there stars, but there's a lot of dust. If you spend a lot of time in Los Angeles, you understand the effects of dust. It's like smog. You can't see through it. So that's the missing light in the middle. That's all the smog in our galaxy. Turns out dust particles are very good at blocking light the size of the dust particle. But if you look at light that's is bigger than your dust particle size, you can get through it. So that's why I work in the infrared. Only 1 out of every 10 billion photons in the optical makes it to us, what your eye detects. So it's a complete screen, which is what you see there. 1 out of every 10 photons, light packets, makes it to us in the infrared. So you can actually see it in the infrared, which is why the infrared is key, which is why I'm at UCLA, because they want to be the premier group for infrared astronomy. Okay, so we're going to look at stars. And those stars are going to tell us whether or not there's a black hole and then provide us with a handle. These are the Keck telescopes. This is a magical, impressive place. This is the top of Mauna Kea in Hawaii. It's not a bad place to have to go to work. This is my laboratory. To be honest, when we started this work, we went up to the summit. This is 14,000 feet. This is not an easy place to work. It turns out your brain doesn't work particularly well up there. So in fact, we've done a lot of work to move the astronomers off the mountain. So roughly 10 years ago, actually 15 years ago, we began controlling this telescope from Waimea, which is where the headquarters for Keck Observatory is. And today you can actually control the telescope from UCLA. So we have a remote observing lab where it is the window into Keck Observatory. It is a unremarkable room, given the remarkable technology that we are using every night on this telescope. So every night is assigned, and as you can tell, it is a valuable, valuable resource. So astronomers work very hard to get access to this telescope. So tomorrow, my proposal for the next year's observations are due. So you know where I'm going after this. Okay, so this technology allows us to see, oh yay, this is going to work. You guys are amazing. So this shows you the technology. So without it, you see a fuzzy mess, and with it, you actually see the stars. And in that central box, that's, which is basically the resolution you would get if you didn't do this technology, you see the stars. And those stars are the ones that we want to watch, the ones to watch. And they'll move faster if there's a black hole than ones that are at the large. Okay, I'm going to skip that. That just says we did the first time, we like that technology. And here's how the most stars have moved over the last 20 years. This is actually a quarter of the real estate that I was showing you in the small box. Most astronomers or astrophysicists would think that this is a ridiculously small area of the sky to be looking at. So this is like an incredible microscope, but it's actually a telescope on the universe. And it's also worth pointing out that when I first applied to do this experiment, I was a new young professor in 1994. I thought I had a great idea for getting tenure. That's all I wanted out of this. They said, no, not only will your technology not work on this telescope, but even if it does, you won't see anything move. I love looking at this movie. Because we have now become one of the biggest users of the Keck Observatory. And this project has now become a key science case for the future of the observatory and the future of the large telescopes the University of California is building. And the key to this animation here, which shows you how the stars have moved, that you can actually probably find my favorite star in the universe. Its name is SO2. It probably needs a much better name. But it tells us, because it orbits around, you can figure out the mass that's inside its orbit. And the size of this orbit is the size of our solar system. So this orbit, which goes around every 16 years, shows us that there's 4 million times the mass inside a size that corresponds to our solar system. So think about that, right? Our solar system has one sun, 1 times the mass of the sun. In the same region, we have 4 million times the mass of the sun's worth of mass inside that region based on this experiment. So that's what tells us that there's a black hole there. And it's also opened up this whole new way of looking at black holes. Okay, so we want to understand gravity. Precision measurements of these orbits are key. The next time this star goes through closest approach is the first time we'll be able to make these tests. What that animation showed you, not only was the passage of time, but what is harder to glean out of that is the development of technology throughout that time period. So our ability to make the measurements has improved by at least a factor of 10 over the last 20 years, which has been a great advance. So time helps us. It's like a fine wine. You just get more data, and your understanding of those orbits gets better and better, but also the precision of the measurements has been getting better and better. So the next time this thing goes through closest approach, which is next year. My group has been 2018 or bust for so long, and bust is next year. I hope not, it's bust or boom, so we're hoping for boom. It will be entree into tests of general relativity that have never been done before. These will be the first such tests that have ever been done. So we're excited, and the physics community is excited. We also want to understand how black holes control the growth of galaxies, because that is a key part of how we think the universe works. And our galaxy is the only place in which we can measure the orbits of stars around a supermassive black hole. So it's the only place in which you can get insight into this fundamental hypothesis that we have about how the universe works. And this is an animation that gives a little sense of our data over the last 20 years, but now in 3 dimensions. We were zooming in to the very central part, which told us about the black hole. Now we're pulling back to understand the galaxy. The thing I love about this at this point is every idea that we've had about what we should find has been inconsistent with the observations. So for a researcher like me, this is job security. There are so many questions that we must understand. To give you 3 very quick sense, the predictions were there should be no young stars in this region. This is a hostile region. Star formation should not be proceeding. That's prediction number 1. Prediction number 2 is that there should be tons of old stars. Old stars have had tons of time to interact and find the life of the party, so they should be congregated around the black hole. So the blue stars are young. They shouldn't be there. The old stars are orange. You can't find them because there are barely any of them. And then there's a pink star in there, which we didn't think to predict. And again, the unknown unknowns are often just as interesting as the things that you thought to make predictions about. So we are having a great time trying to get to the bottom of all these things. We're advancing new technologies, which means we're dreaming of shining not only one laser, but multiple lasers into the atmosphere. I can talk about that more if you're interested. And we're working on building, the next generation of telescopes. This is a $1 billion project, if I can go back, but maybe I can't. You only get a peek. It's a $1 billion project that is also supposed to be built on the summit of Mauna Kea. It's a UC Caltech, Japan, China, and India project. It is a fascinating project, and this Orbits initiative is one of the key science drivers for this $1 billion project. So if nothing, I hope I've excited you about astrophysics this afternoon and convinced you. Yeah, I'll take it. Thank you. All right. Yes?
You really care about big data.
Yes.
There's a lot of people in this room who really care about big data.
I would imagine.
Is there much cross-fertilization that's happening? Do you look out into industry and say, that's cool, we want to do that? And do you lose your top scientists to the industry?
I would say that we're only recognizing recently, because we started small. Remember, I started with very small data sets, and it's grown, and the size of the data sets and the kinds of things that we can do have grown. So I've only really recognized in recent years that we're big data. So the main thing that happens is I lose my students to companies. But we're starting to get smarter in terms of now trying to hire people who are trained as big data gurus, and working with people who study big data sets. So there's a center at UCLA I've just discovered, and we're collaborating now on the Center for Knowledge Infrastructures. So in other words, how do you best manage big data sets? So we are effectively, I don't know, maybe the corporate or the industry analogy in terms of what we're doing in academia. We're the small company that started in somebody's back garage. And we have definitely grown a lot. We have a data set now over 20 years that is effectively a $40 million valued data set. We need to think carefully not about how to build the infrastructure to care for this valuable and unique data set so that we can continue to do the new kinds of science that this long-term data set enables us to do, and to develop the tools for completely mining. I would say we are underutilizing the information of that data set to high order. So we're just now getting into that business of being smarter about the data. So we'd love to talk. Yes?
You mentioned that some of your work increased the certainty around the supermassive black hole hypothesis, 10 million.
Mm-hmm.
Amazing. We can't prove then right now. What is, if there is any, what is the most compelling alternative hypothesis for what could be the cause of gravitational effect being attributed to supermassive black
So the particle physicists got quite excited about alternative ideas. So I proposed the idea that it could be what's known as a fermion ball. So it's an extreme form of matter. So the idea here is that the black hole would be completely a pure object of fermions. So if you think about atoms, atoms are nuclei and electrons. So in astrophysics, we know we can already ionize, get rid of the electrons, and we can already break up the nuclei into protons and neutrons. So there are neutron stars, which are pure neutrons, because all the protons join with the electrons and make a neutron. So you get a sea of neutrons. So this is going a step further and breaking up the neutron into its fundamental constituents, which we've never seen in an astrophysical object. So again, it's allowed, but you have interesting constraints now on what that mass of that elementary particle is, and there's no theory today with these constraints that can produce the particle that can explain all possible supermassive black holes. So it is, there is wiggle room, which is what you're getting at. We haven't gotten down to the size of the Schwarzschild radius, because the size of the solar system is further out. So we did make a jump of 10 million, but there's still a sliver. And of course, as scientists, we fill it rapidly. But the future will put better constraints, because again, time just helps you.